All right, so here's a quick look at the solution to this first problem this week. The first question says, draw and label the forces that act on the spacecraft. So the spacecraft is moving in this direction, but there's no force on it. The only force present is the attraction due to gravity. So you need to have an arrow going in that direction, and that is the force of gravity. Okay, and that's worth 2 points. 1 point for an arrow pointing in the correct direction, and 1 point for labeling it. You can write the word gravity, you can write weight, but it has to be labeled, and that can be the only force acting on it. All right, so that's 2 points. Part B asks you to derive an equation for the orbital period t in terms of the quantities that are given and any physical constants. So you start off by realizing that when something's in orbit, the force of gravity is equal to the centripetal force. And the force of gravity is G big M little m over r squared. And that equals the centripetal force, which is little m v squared over r. And this is little m because little m is the mass of the spacecraft, and it's the thing moving in the circle. Okay? So realizing that this equals this got you a point. Realizing that the velocity is the distance divided by the time, which is 2 pi r, that's the distance it goes in an orbit, and t is the orbital period. Knowing that gets you a second point. And then being able to substitute that in for v here and work out an equation like that, or even if you just had t squared equals 4 pi squared r cubed over g mass of the Earth. If it wasn't solved for t, it was solved for t squared. That's still acceptable. So you get a third point for substituting that in, even if that's as far as you got. Although that's the right answer, and that's where you should be headed. Okay? So that was worth 3 points. So you've got 2 points here, 3 points there. That's 5 points, and there's only 7 points on this problem. All right. The last two parts of the question. A second spacecraft with a mass 2m is placed in the same orbit with the same radius. What will happen to its period? And so the answer is it's the same because the mass of the spacecraft canceled back there in our derivation of the period t. So it doesn't matter. Okay? So it's the same if the mass is double. Lastly, what happens if you go to a larger orbit that has a greater radius? Well, you've got to go back and work out how does the orbit radius depend on the velocity. So from part 2i, or 1, we know that gmm over r squared was equal to v squared m over r. The m's cancel, and that r cancels that r, which leaves you v squared is gm over r, or v is the square root of gm over r. So this tells you the nature of the relationship. As the radius increases, the velocity decreases. And so checking less than with a reasonable explanation got you the last point. So these last two things were worth 1 point each. This was worth 1 point if you had equal to and a consistent explanation. And this was worth 1 point if you had less than and an explanation showing that the v and the r are inversely related in some way. Okay? So that was worth 7 points. So that's how you solve that problem. And it wasn't too bad because we've solved a similar one before.